All right. So hello, everybody online, and hi again to everybody who's here also. So today we are doing this session where we're going to have 3 parts. I'm going to run this for the beginning, and then we're going to sort of take turns. We're going to look at a series of notebooks that you will find, in fact, for the most part, already within the Docker image. They're coming from this web page here, which is the JuliaEO notebooks web page. So if I show you on GitHub, the information about this is in a README file now within the repository of the workshop. So this is a, sorry for that. This is just to show you the JuliaEO organization as it is. It has a bunch of packages in there that we're going to use. And at the top of it, it has this notebooks link. So the notebooks links give you this web page. This is also where the Docker instance, that the Docker image that we're using, in fact, comes from. And so these go together. And if you scroll down in this page, you will find a long list of notebooks. We are going to focus on a couple of them. They're all Pluto notebooks. And the way this works out, for example, I'm looking for one specifically. Sorry. Yeah. So the way this works out is you have links to the notebook itself. So if you have never seen a Pluto notebook, this is what they are. There you go. So the notebooks themselves are actually text files. They have a lot of things that you've already seen, like these using packages at the beginning. And importantly, at the end, the Pluto notebooks contain their own list of dependencies. And so that's one of the reasons why they're very practical. You give the name of the file or the URL to somebody, and they can reproduce it. So in this case, for example, we're going to use packages called Kairomaki, which we talked about yesterday, Ocean Robots, and Pluto UI, which is going to give us interactivity. So in this web page, if you grab this URL, you will be able to put it inside of the Pluto command line. I'll do that in a second, but I want to show you also the rendering of the notebooks once they are processed. So this is the sort of things that we should have at the end. Once it's run, this is the static HTML version of it. So this is not interactive, but this is once the notebook has run. All right, so then what do I do next? Okay. So this is our Docker instance, the same one that we've been using. I have, in fact, started a bunch of the notebooks beforehand, so I did not have, so that I would not have any latency. But the idea again is if you're in the, so all of those are open. So this one is already open for me. But like I said, to open a new notebook, you take your URL and just paste it here, and you click open. The other thing I want to show here at this point is, in fact, a bunch of the notebooks are already there. So you can get them from file. For example, they're all the one I'm going to use in this notebooks folder. And then say, Ocean Robots is the one that had the one I was looking at. Oops. And so this is here, and you do enter, and it's going to fire up, right? So this is how Pluto notebooks are operated. I'm going to get maybe one that I have not started to show you what you might expect. Let's see. Let's do this one. When you open them, there's going to be a little bit of time that's going to take to run every cell, essentially, unless you do a special trick. And so right now you're looking at a page where, in this case, you're seeing that this cell is getting evaluated. So these are all of the packages, the Julia packages that are used in this particular notebook. So here, the same one we talked about, except there's also geomachy, data frames, JSON 3, and HTTP. And the reason why there is that this notebook interrogates an API from something I will talk about a little more tomorrow, which is somewhat related to the concepts that we talked about with MBORN in terms of coordinating the global observing system, something called OceanOps. And so this particular notebook is going to give us the current coverage by floats, the planned cruises at sea, all sorts of kind of oceanographic operations that have taken place, are taking place, or will take place. There we go. So this is, for example, what you get from this API of OceanOps. I'll talk more about this tomorrow, so don't worry about it, but I wanted to show you the latency of the notebook is going to load. So that's why I preloaded all of them. And so I'm going to start now with the gridded data story. And then we're going to go through a few of them. So let me start here. So gridded data, the grids can be simple or they can be complex. In general, the more broadly used data products tend to be on a lat-long grid because that's very simple to use. People know how to plot it immediately. And so we end up doing that as well. But in our case, that would be for the modelers, but also for the satellite people, we start generally from a different grid that's more convenient to our needs. So I'm going to show you a little bit where the sort of hoops that we jump through with this kind of complex model output. The point is not to worry about it. This mesh arrays package is there specifically to handle the kind of output I'm talking about. One more thing about Pluto, you can hide the code, and by default, I tend to hide it such that I can just tell you the story and show you the code when I need it. So if you wonder why you don't see more code, it's because it's hidden from you for communication purposes. The Julia packages used in this case, I've already mentioned it. Nothing particularly complicated. So this tutorial is going to take a set of gridded output from this model that we use with the NASA project called ECHO. And this is out of the MIT GCM, the MIT General Circulation Model. This is an example here of a gridded domain. I think I'll probably play with this. This didn't react, okay. So we have a gridded domain, and then we tend to split it up in different tiles that we tend to call them. So here there is 8. If I change this, should be less. No, I'm getting myself confused, so never mind. Why do we do this sort of domain decomposition? Well, it allows us to put a model on a distributed computing platform where each processor does its own thing on a subdomain. And this is an example of the kind of grids that we end up using out of a cube sphere. So for example, you might see here that this looks like America, both North and South America, except it's weirdly oriented. This is Antarctica, right? And so the whole sphere is discretized and split up in this sort of strange way. Again, don't worry too much about it because we're going to simplify that at the end by interpolating. This is the one that we use for the global model. So instead of 6 faces of a cube, it has 5. Never mind. The point is you do interpolation and now you're safe. You're in your usual space. So the interpolation in my case comes down to this function. The mesh arrays package essentially is something that has a subset of the capabilities that you would like to have in terms of geospatial analysis more broadly for gridded data. But very specifically, it's targeting a set of configuration and grids that rather than trying to solve the general problem. And so this little function is sort of similar to what you will find in other software. You sort of look within your grid cell, do a bunch of polygon operations to figure out where you are, identify grid points, get coefficients, and then you interpolate. By the end, you have this sort of things. And now we can go ahead and analyze things in a much simpler way. So this is the sequence of operations for the interpolation. So this, maybe I should make this a little bigger. This here, right? This variable is the interpolated one. So that is just should be just a flat array. Maybe I have too many notebooks open. It will show up, I think, eventually. The rest here, I don't really need to talk about. I'd just like to see this this array. No, it's not cooperative. Anyway, so I'll move on to the next topic in this case, which I should have here. How much time? So there is, in this series of notebooks about the gridded arrays, you will find 2 more. One is called, I'm going to open it now, I guess. Geography. So geography is going to be taking this sort of output that's been now interpolated and easy to use, and it's going to display it in a projection type of framework. I will let this load, and I will get back to it afterwards. There is a vector one. So by vector, I mean something slightly different than you would in the geospatial context. Oops, sorry. I'll open that one too. And I will explain in a minute. I should be able to go to here and show you how it looks at the end. If I can find it. There we go. We shall see. I need to bring this one over there. Oops. We do have here, for those who have not been with us, a Wi-Fi that is relatively slow. So it might be interesting to see if it computes faster than it displays from the URL. Let's see if the geography one did anything. Still computing. Okay, I'll get back to this if we have more time. And I'm going to, oh, there we go. So you see this little bar at the top. This is showing you the progress in terms of computing the entire notebook. The idea is that it's just going to compute the whole thing and then you can play with it afterwards. And I don't know how much interaction there is here. Yeah, there's a little. Come on. So we are racing the Wi-Fi against Julia at this point. I think Julia is going to win. There you go. I should say it's not just Julia. There is the Docker instance running on my laptop, and there is like 10 notebooks open. So this latency is a little overestimate. So just to illustrate the sort of things that we can now do with also GeoMaki is we have ways to, plot things in the ways that you might want to do that. The simplest is, of course, the lat long grid. But then, there's all sorts of projections that you can access. And I think in this case, I did it through just a projection package, but it's now built into the GeoMaki package. This is to illustrate something that we often need to do in our climate applications. We want to compute something like what I discussed before, ocean heat transport. So what that implies is you're doing the line along the grid, and then you're going to compute the integral of the vector flow fields across that grid. So you need to be able to figure out how those lines work out. I'm going to do a little change here to see it. So this is the little algorithm that figures out if I give you 2 points, this one and that one, that defines a great circle around the Earth. There is only one. If you do a small circle, that's defined by 3 points, but this is a great circle. And then you see some staggering. That's because we are following the grid lines along this complicated grid that I talked about at the beginning. To show the structure of the grid a little bit more, these are for one of the faces of this 5-phase strange things that I talked about. These are the area of the grid cells. So you see that they are heterogeneous. Blue here is smaller. It's in units of log of meter square. And if I change this to say the case number 3, should be the one that's over the Arctic. You sort of guess that there are 4 corners to this array. Oh, I see. And I'm going to keep going. Let me do something else here, just to show you we can retile this domain, and we can sort of move around. So we can break it down into smaller pieces. We can do things like that. Change the size. So these are the sort of functionalities that are built into mesh arrays. And then we have basin masks. Those are the type of things you would do more generally by giving a polygon. And that's one of the things we could do in the hackathon. Here they are already pre-baked. So, and then we have also other things like that, like definitions of all of the major straits in the ocean where we want to know transports. So that lets us go to the vector part, which very briefly has crashed. So I'm going to go back to something else. And now to the notebook that was, what am I looking for? Yeah. I just wanted to go back to MBON. And so here what I did is I took a couple of the polygons that I found on the MBON website. One of them has this, I believe it's a seascapes climatology, but the metadata was not on the website, so I'm not entirely positive about that. So this is one of the polygons that I have available. Another one is this one. So these are the exclusive economic zones. You're going to see a few more regions. And for the hackathon, one of the activities we would propose to do is to take the exclusive economic zones around the Azores, and then gather a bunch of data in there through some of the packages that we talked about before. All right. Yeah, there's a few more because every country has one, or every country that has a coastline has one. Come on. So this notebook uses the GeoJSON package to ingest the polygons. It uses GeoMaki to display along with CaroMaki. Any interactivity that you see when you see me clicking buttons here in these notebooks, it's coming from the Pluto UI. And then Dataverse is this API that I overloaded in Julia essentially to interrogate the database. So Dataverse is a data archive. I'm not going to illustrate it right now, but tomorrow we'll talk more about it. It can be integrated through both a REST API and a Python API. And what the Dataverse.jl package does at this point is not much more than just calling those from within Julia. Right, so here are the exclusive economic zones. So I'm not going to say more about this one. Yeah, except that there is Python dependencies that are getting installed on the fly. So it's an example of this notebook I think of integrating a bunch of different packages from different organizations that we have already talked about, from JuliaEO to JuliaGeo to Julia Climate and so forth. And what is the gathering data? Yeah. Okay. So the last thing I'm going to do on this one is sorry. No, that's what I'm going to do on this one. So now we're going to move on to the second topic, and I think Adriano is going to, Andre is going to pick it up from there.
Hi, everyone. So this is going to be actually just an introduction. Gael will just follow me soon, because the idea here is just to show you some examples of the oceanography data that you can get from satellites. So one of the most important products for oceanography, operational oceanography, is the sea surface height, which is measured by altimeters. So it measures the height of the sea surface. So it's the anomaly, basically. So the ocean actually is composed by hills and valleys. What you are seeing here okay, so this is going to be frequent. What you are seeing here, the valleys are the blues, the hills are the red, and this is from satellites. And in the red ones, the water moves clockwise. And in the blue ones, it moves anti-clockwise. And in top of it, you have floaters, and you have two types of floaters here. And by the way, this is in Azores, you can see, and you see the mid-Atlantic ridge. So you have two types of floaters currently available freely. The ones that have a round shape are the floaters at the sea surface. These are basically driven by wind at the surface, so they move much faster. And the square ones and the triangle ones are actually Argos. So these are at around 1,000 meters, and every 10 days they come up and they take a profile. So you will see that the circles move quite fast. The others don't move because they are at 1,000 meters. And you can see in several occasions that they follow actually quite well these sea surface anomalies. And the other thing that you can see is that the mid-Atlantic ridge, you can see sometimes the floaters coming from the west, and they basically stop at the mid-Atlantic ridge, and they kind of get stuck somewhere in these areas. They just, if they cross it, they either cross it very fast or just stay there for a lot of time, bumping into this area. And it's quite interesting because these surface floaters are at the surface, and it's about 1,000 meters depth, these bathymetries. And the idea now is that to make these in Julia, and there are several packages to make these, and Gael will give you a short presentation on that, and then I'll be back after just present the other topic. Yeah.
All right, we're back. So next notebook is this one then. So this is what I've gotten to so far in terms of reproducing this in Julia. So you're seeing again sea level anomalies and then contours that are the topography. So the ones that are most concentrated are the islands. And then you see also the shape of the seafloor. So this is the Mid-Atlantic Ridge. These couple lines here, I opened them up to highlight the way that this Dataverse app API works. So you get a URL, which I'm not going to try to open this in the web browser, which is going to lead you to a web page on the Dataverse site. By providing the DOI, you get a data frames out of there, which will then give you a list of URLs via this second command. You can now select files. And if you're running this particular notebook on your instance on your container, this file might actually be missing. So you might get an error. And if you were in that situation, the notebook might complain. So you can change this and it should download the file for you. I have also put the files on the USB drives for this notebook. So you should be able to replace the path, which you see here, with the one that leads to the USB drive via the USB drive or via what you have now put inside of your container. You should find a set of files that are going to be, in my case, I've put them just here. There should be this file called SLA PODAC. This is the NASA version of altimetry of the sea level anomalies. CMEMS is the Copernicus version of the same thing. So we're going to be able to switch between the two. And this TIFF file is the one that has the topography of the seafloor and of the Azores in it. This last file is a NetCDF file that will give us the drifter datasets. So to make the notebook work, you want to have this path here, find your data folder, where those files I've just mentioned are. If it's not found, the notebook will download automatically, but because of our sort of slowish Wi-Fi here, that's going to be difficult. The people online should have less trouble with that ultimately. And so, well, I want to see, it doesn't matter. So the point of this notebook is to show you that we can already redo a fair amount of the work in Julia with just what's available to us in terms of packages. I've put a little thing there to switch. Doesn't seem to be doing anything though. That's strange. Maybe the notebook kernel died. So here you're looking at the code that just selects based on the value of this file that you get from the widget.
Just one question.
Yeah.
Which notebook are you running? Because I'm trying to figure out Everybody around me looks like they're not.
That's totally fair. Sorry for that. I am jumping around a bit. There is one that's called satellite altimetry.jl.
One that's on the Julia GitHub, right?
Yeah. So if you copy the URL, sorry, I totally forgot to say that. Thank you for the question. So I think it's, is it here? I need to find it myself. Okay, I just passed it.
It's on the grid of data.
On grid data? Here? Sorry.
Data sets.
Data, okay.
Yeah.
Okay, thank you. Yeah, so it's this one here, right? And so you want to get the URL. Yeah. And you want to grab the URL, not the HTML link. Go to your container and paste it here. I'm actually going to do that as well. So I'm going to be running the same notebook twice. That's okay. And so it's going to start showing up like this at the beginning. It should. And again, there is this little orangey thing over there that tells you how far along it is in pre-computing the notebook. Yeah, no, please interrupt me if you have any questions. This is the hands-on session, and I have a lot of things going on, so I'm forgetting things. Since I'm looking at this, the links to the data are here also, right? The data sources are included in the notebook. So if you click on this link, you will go to the topography that I've used. So I extracted a little piece of the so-called eTopo dataset. Woo. And this is the link to the NASA webpage for the sea level data, and the corresponding one from ESA, from Siemens. So what I ended up doing for preparing this notebook is I took these data sets that are global and I just cut out a piece so that you have a file that is not overwhelmingly big. Either one of those. Yeah, so I already had the files in place, so the notebook went fine. And if I do this, it should not be active. So you're going to see the resolution is going to change a little bit. I think one of the two data sets is daily and the other one is 5 daily. And their spatial resolution is also changing. So I think the one that is 5 daily might be the Siemens and might be higher resolution in space, whereas the daily is the PODAX or the NASA one, and then it's going to be daily. And right, and slightly coarser. Come on. Oh, no. There is in there a time series. So once you, I'm not going to touch this because otherwise it's going to trigger another computation. Once we have this file, we can cycle through it and then make a little movie. And so I have rendered the movie so that we would go faster and see it during the time of the presentation. This is the command that will regenerate the movie. I will fire it when this is done. Maybe the other copy of this notebook is already at that point. Probably this one. This was the first one. Oh, it's also computing. Okay, I'm going to kill one of them. I'm going to kill this one. Okay. So that's kind of what I had for this. Since this is computing and I might have a few more minutes, I'm going to go back to something I meant to show you in the first part, which was the climatology data from this biochemistry and ecology model output. So one of the things that I like to build with Pluto is interactive visualization like this. So this is just a notebook. You see zero code because it's all hidden, but then you see a bunch of widgets, which if I did not damage the, yeah, there you go. So this is running fine. So this is chlorophyll, for example, and you can just, go through the month. You can change the variable to something else. So let's say PAR, which is the photosynthetically available radiation, if I'm not mistaken. And so you can explore, the different wavebands of the satellites that we have translated in these remotely sensed radiances. There is something for salinity, so this would be that. And then there is a little bit more, which is this widget that lets you select a region, and then it's going to build a seasonal cycle from it. So from this notebook, we can generate little time series like this. And for the hands-on session, one of the things we can do is generate a little CSV file from that, which will give us a kind of a bunch of covariates over time. And we can start training things like a neural network with the flux.gl package we used before in the week to predict one variable from the others. Or we can try do a, another sort of machine learning exercise from that. And then you can do a few more things here. I don't know what this is. This is again selecting variables. Right, so then I guess the region I picked here was interesting. Let me go somewhere else. Right, so this reactivity that you see here is just baked into Pluto. And that's one of the reasons I think it's a really nice framework for communication. Jupyter has its own advantages, one of which is it does not require that the whole thing runs first, right? So in some cases, that's what you want. But for like interactive presentation, I find that both Mackie and Pluto give you options like this that are really nice and pretty easy to build. Typically, this is how you build the widget in Pluto. You just give it this one line of command, and that's it, right? At the end of that, you have a reactive feature, which is this variable that's going to propagate through the notebook. So it's extremely straightforward, I find, to build things like this. Coming back to my little thing here, has this actually? No, still hanging. Okay, never mind. So maybe I should leave it there for this part. No, I need to do one more thing, sorry. Oh, I do have time, okay. Good. So the next thing I wanted to show you for this part is the drifter data that Andre mentioned. So this is from, there's a link to the NOAA webpage, their FTP server. This is a globally coordinated effort to collect observations of velocities in the first place, but also temperature at the sea surface. So this is buoys, you see them here. And this is one of them being put in the ocean, and then it's going to go around. It's going to follow the ocean currents. And on the left, you have kind of an example of a map of what those look like. So here is one of them that I've grabbed. I'm going to click on that boldly and see if it gives me what I want. But meanwhile, so you see on the left-hand side, the time series of the positions of this buoy, float or drifter. there you go. So this is another one. So you might have noticed that it's very different. This case, right? The drifter went, this is in the Southern Ocean, I believe, and it's following the so-called Antarctic circumpolar current, just by eyeballing it. So you see that this drifter went from 75 degrees of longitude all the way to 175. So it's cruised around a third of the circumference of the Earth. And on the right-hand side, you see sort of the velocity estimates you get. These are the sort of time series you can build from this. And the first one we had, which I think was this one, instead only moved by about 20 degrees of longitude. And you see all of these sort of circles here. These are features in the ocean that are called eddies. They are the counterpart to your atmospheric storms. And that's what I was going to say on this. So we have access to these data sets through various ways. In this case, I'm using, again, standard packages, and I'm sort of doing the rest by hand. I have another notebook for this, which should I do that? I have another notebook for this, which I'm going to grab from the URL. Ooh. So I'm going to go back to this web page. And now we're going to look at data. Okay. So this one is actually not linked here for some reason. I forgot to do that. So I went to the GitHub repository for this. So this is in the Julia Ocean organization, Ocean Robots. .jl. If you scroll down, you're going to find this little markdown file that has some folders in it. Yeah, I should say I tend to do that. I like foldable things in markdown. And so if you go to surface drifters, you're going to find this first one we just looked at. And then there's this second one, but I'm going to get to it because I want the URL of the code itself this way in the examples folder. I want to grab this one. So this is a more recent approach where colleagues at NOAA and associated institutions have been working on reformatting this data set to make it more easily available via cloud computing means. And also, I should say that this is a data set that has been processed such that it is at hourly resolution. So it, and it has SST at hourly resolution. So that's kind of unique, in fact, as far as I know. This is a data set that's going to have kind of quasi-global coverage and give us the daily cycle of temperature. That's kind of a hard thing to get to. So this one, I might not let it run all the way through, but it's going to interrogate this new format that they have. And it will, if it completes, oh, no longer running, okay. Okay, maybe I have too many at this point open. Okay. I'm getting myself in trouble. Let me open that again. Oh, it died. Okay, so it killed all of my notebooks, probably because there's a memory limitation that I did not pay enough attention to. So I'm just going to open it again. So this is a notebook that I adapted from somebody else's Python notebook that was from an effort funded by NASA. they have reformatted this data set such that it's now, instead of one little netcdf file per instrument, it's one big file, but it can be chunked and it can be accessed in a way where we're just getting a piece of the data set. And the next iteration of this, which we can look at later on in the hackathon, is that they are now putting this on S3, Amazon Cloud Services storage, so that you can then access all of this. Let's see if I get to do that. Oh, what's up with that? I see. Okay. Let's start the notebook. Yeah, let's do that. So call this one. So I'm trying to locate my data, right? Struggling a little bit. Should be here. This is weird. Oh, just so once you have the right path here, and that's the file that I've put in the on the USB drives, this GDP subset file. This particular notebook should then run. I did this preparation of a little file again to avoid having to get you to download more. So I sort of pre-canned everything. Now, the way this is set up is a little more interesting than the previous one. You get the data in a format that is a data frame with a Cartesian index with time, latitude, longitude, the SST variables, so on and so forth. And then what I did in this notebook was just replicate what the original authors had done. So again, if you go to this link here at the top, you will find the original notebook. So this is taking this data frame and then just grouping it by the indices, the Cartesian indices. And that's kind of all you have to do to get to a map like this, where you have sort of rasterized your data set, essentially. And so I have a little helper functions at the end. Group by is just data frames.jl. I'm going to show you the other thing here, which is to grid. So this is just, you call the combine function against this straight up data frames.jl. And then there's just a tiny bit of post-processing to the average, I guess. To map the result of the combine operation, which is this df2 variable, a new data frame, to map that into an array so that I can then plot it. So in a way, the rasterization of these in situ data sets is greatly facilitated by data frames in itself. And we have seen this week solutions from rasters.jl and from other packages in the JuliaEO organization that will provide you with more elaborate and powerful methods, streamlining this process. The next thing here that I'm going to show you is this little command. So that's the one we're going to want to modify in the hackathon, for example, to get to the Azores region. Here, what I did was, or what they did, in fact, I copied it from their notebook, was I think a region in the Gulf of Mexico. And so this selected the trajectories from this big data set between two dates, so 20 years of data, and just extracts the subset, which is this data frame you see at the top, which is significantly smaller than this one. So this is the whole data set, it has about 5 million points in it. Once I go to my subdomain, I have 23,000. So if somebody in top of their mind head knows the coordinate of the ASOS, we can put that in. I just don't know that. So let me just do. Just going to go. All right, let's go a little more north. Okay, so I have 25,000, and this is what I'm getting instead. So we will need to, verify that it's quite close enough to the regions. The idea would be to take this for a particular time period and put it on the map that we had seen before and combine the two. It might not have the whole time series, now that I think of it. So we might not be able to do the animation just with this subset. But if we had the global full data set, we should be able to then do this in sequence and build the movie like we see at the beginning. What else about this? Yeah, just so the notebook by my colleagues, Shane Elipa and the people working with him, also included the computation of the frequency spectrum. And so this is what's shown here, replicated again in Julia. So it's mostly highlighting that we really know how to do these sort of things. So this is, this is just this computation basically. And then the rest is the plotting. Gives me a quick, opportunity to show you the Mackie code that plots, straightforward, right? And then FFT shift is from this FFTW package. So again, illustrating that in the Julia ecosystem, we have a lot of what we need to do state-of-the-art science today. I think I'm going to leave it here and hand it over to look at the Merida use case. Thank you very much. I hope this was clear enough. Sorry that I'm sort of bouncing around so much. Might have been a bit too bold on that.
Everyone, just a second. Okay, so now we are going into another hands-on. It's the random forest classification with Merida. I hope you all have the folder. There are 3 USB around. Who doesn't have it? Just say it, we will pass to you. So in that folder, you basically have the Julia, which you have to enter in Pluto, that one, and you have to put that input data folder into your data. Sorry? Sorry. No, I cannot. But if you need the pen drive, yeah, there are 3 pen drives around. You can ask. So you have two folders there, inputs and README, and this is the Julia that you will need. But I will come to this after, just for you to know beforehand. So what we are going to do is a random forest classification into a Sentinel-2 image for a special case, which is the detection of plastics, floating plastics accumulations. What you are seeing here is an image from Honduras, and so this is optical data. We have been talking about altimetry and also SAR. I think this is the first time we actually talk about optical data. Sentinel-2 measures reflectance at several wavebands in the visible and the infrared. And this is the RGB picture for this particular day in Honduras. You see several features. You see a turbid plume. You also see land. You see ocean. You see some boats. You see clouds. And you don't see it, but along the front of the river, around here, you can see some structures bright. And what is this is those carpets of plastic. So this is a very affected area about plastic pollution. Every time there is big river runoff, it's on TV. You might have seen it before. I have provided some links in the README folder so that you can see. So what is Sentinel-2? What is this Sentinel-2 image? So basically, you have reflectance in several bands. The B1 is blue, green, red, and then it comes into the infrared. This is so reflectance is the satellite is seeing the sunlight reflected at the surface and also in the atmosphere that is reflected upwards. So the sensor is measuring this reflectance. Is basically the amount of sunlight reflected on the sea surface. It measures this at the top of the atmosphere. So to reach the reflectance at the sea surface, you have to make several processings, namely atmospheric correction. And there are two main components, the Rayleigh correction and also aerosol. The Rayleigh is the most easy. The aerosol is the most difficult because it's quite variable and we don't have enough data to do this. So it's a step, it's one of the most difficult steps. So typically you can use this one or the top of the atmosphere reflectance easier. And one of the reasons why we are using Rayleigh, it's because the spectral library I'm going to show, it's also Rayleigh reflectance. We did this, so we download this image, we processed it with the Acolyte atmospheric correction to get this Rayleigh reflectance. And then we apply already some masks. So in the input folders, you will have the geotiffs already masked, something like this. We mask the land, we mask clouds with another algorithm, and we also masked most of the pure water, the marine water, the water that doesn't contain nothing on top. There is nothing floating. It's just you can do this by the reflectance. So basically, these are the masks, just for you to understand. The land mask from well covered, the cloud mask from S2 cloudless, and the clear water mask. In the left side, everything is considered clear water except the turbid plume. And also you can see those filaments in the center, which are the supposedly plastic accumulations. And so you get these. We are just going to process these pixels in blue. And so the objective is to get something like this, where we have a classification in each pixel of what corresponds. In this bottom, you see the masks. I did it with some different colors for you to understand. You have the sediment-laden water in the mouth of the river. You have some false positives of floating organic matter and floating sargassum around the clouds, because as you can see, these are nearly transparent clouds. So they are quite difficult to, one way is just to increase the buffer of this cloud mask that will take most of these false positives. But I'm leaving them here so that you understand. And then in the end, you get these classifications of plastics around here. And we also have other classes like foam, pure marine water. These ones are actually from the mask marine water. And this is so how do we do this? We do this with the random forest. We actually did a notebook for this hands-on, which is that one. We have this workflow and we just adapted these steps for Julia. What am I going to show more? Okay, so here in the inputs, yeah. Here you have just a brief description of what I said. we will train a random forest model using Merida spectral library. Okay, so this is the quite recently. Yeah, this one I can. Okay. Better? Okay, I'm just going to explain you. So this is the spectral signatures from Sentinel-2 of several classes. Merida provides several classes: clouds, sargassum, foam, marine debris, marine water, sediment water, ships. So basically, the challenge is because you have a lot of overlapping between classes. And for example, plastics, marine debris, which you see in red, it's quite close to several other features. So the challenge here is to use machine learning to try to understand from each pixel which class it is. You can read this to understand. You have this event. You can see the movie. You can see these carpets of plastics. And so this is the image. And so basically the inputs of this notebook will be 2 text tables, train and text, where you have the spectra for each class. There are thousands of spectra for each class. And we already modified this a bit. We made the super classes and we removed some other classes just to make it faster and easier. And then you also have the explanation I told you about the mask. Okay, so this is what you've seen before. And now Emmanuel is going to give you just a quick overview of that notebook, which we could try to also tackle in the hackathon if you have interest. Okay, Emmanuel, come. I think we are on time.
Is it big enough for everyone? So hello, everyone. My name is Emmanuel. I will present here a short Pluto notebook about the random forest classification using the Merida dataset. That is a huge marine debris dataset with around 800,000 spectral signatures extractions. I am expecting that you have already the notebook on your computers. And I hope too that the data is circulating on a USB stick. I can show a bit how my container is, the setup of my container, because I did a small change in here. I am linking the data folder, but also another one that I called other notebooks. So because the notebooks are always changing, I put them in here, and the data I'm putting here. So I have the data of everyone's notebooks, and I have mine that is called inputs. And inside inputs, I have the bands indices of Sentinel-2 that were pre-processed, as Andre explained. And this will be your example image. Inside the train and test datasets, I have the train and the test that I also pre-processed, because if I use here 800,000 points, this would crash from time to time. So I reduced to 20,000. So before running the notebook, you will need to check the path, the initial path, to see if inside the data folder you have the inputs folder with the bands, indices, and the train test datasets. At the beginning, the the Pluto notebook will need some time to precompile the packages. The packages are here at the end. So I'm using data frames, data frames to work with the data that I load from the CSV. ArcGDAL, but okay, this week I know that rasters GL maybe can be a good option. Decision tree, images too, and Maki also maybe it's a good option for here. So is the notebook of anyone loading? Still loading? Yeah, this can take some time. Yeah, the directory is home Jovian data. And I'm assuming that you are putting the inputs inside the data. The inputs folder inside the data, like this one over here. Data, inputs. In my case, the notebook is on another folder, but can be on data too. So going to read the train and the test data. So I'm reading here the both CSVs. Here I'm just visualizing one of the data frames and only the hat 5. That includes some of the bands of Sentinel-2 and some indices that were spectral indices that were pre-calculated, and the class num. For example, for this first observation, it's this class for this spectral signature and for these indices. This is something that is already in Merida and ready to use, only need some changes. Here I prepared the train and test data. For the train, I removed the class num because the class num will be included in the Y train. Here I didn't do a cross validation. This also can be done to choose the best hyperparameters. For this, you will need to split into a third data set that you can call the validation. Yeah, the test data 2, just to plot a confusion matrix to check the accuracy of the model. As I said, I didn't use cross validation in this example, and I used some of the hyperparameters that are used in Merida, like the number of trees, the max depth. Here, not taking too much into consideration the overfit. And this step here is the step that can take more time processing, and sometimes can crash Docker. And if it's happening to you, you can run on your computers. That maybe will be better, but this takes some time to train. Here I'm just applying the train model to the test data to then plot a confusion matrix. I created a different function that I didn't include here that creates a confusion matrix that is normalized and it is in a heat map. Because I was struggling to find a package that have a confusion matrix function ready to use. I think I found one called Lighthouse, so I needed to calculate on my own. At the beginning, this was using Python to calculate this confusion matrix, but then I changed to this one that is not normalized, but that you can see here, that presents quite good predictions or classification of the classes that I will tell you. Here, some of the, for example, oh, not here. Okay, that's here, for example. Here, for example, I created a prepared data for classification that I will show you later, this function. And what this does is reads all the TIFF files that are on your example image, Sentinel-2 image, and does some preparing that includes the conversion of types and not the numbers too. Yeah. Here, because of the removal of the not the numbers from the data frame, because some packages have problems predicting when the data frame has not the numbers. So I remove them. And to not lose the geolocation, I created an index num column. So I removed the rows of the data that have the not the numbers. And for example, the index column is 1, 2, 3, 4. If I remove a not a number on 3, it will be 1, 2, 4. And then after prediction, I will add this the index column again. It's just a method to not lose geolocation. Maybe there is another one that is more efficient, but this was the one that I found to work on my code. Yeah, because here it's the global data frame. Let's say that it's the number of pixels that our example image has. It's quite some. And then I need to predict that image, but without the not the numbers. And this is what I do here. I filter the not the numbers, create the index column, the index num column. Yeah. And then the number of pixels to process that will be reduced. This will be the number of pixels to process. So now I'm here, predicting the image, the example image. It's quite fast, 36 seconds. Maybe yours is still compiling. Yeah, because of the packages. Yeah. And I will show this some of my defined functions below. But for example, this one creates the scene classification map. And here enters the number of global pixels, the index column, predict. And then it's just to save this this scene classification map as a raster. And here I'm just doing a simple side by side of the RGB and the classification. This plot, I didn't put coordinates on this plot. Maybe it will be a good idea to put it. And also, maybe this is a thing that can be leveraged by Maki. Yeah, it's over here, the marine debris, but it's a bit small. Oh, it's small here. Yeah, but it has the sediment laden water, well classified. Because this is a river, it has some vegetation too. The marine water, and here, as Andrea explained, because of the clouds can interfere with this. So passing to the some of my defined functions, like this one of the scene classification map. I try to document them as much as possible. Yeah. As it says here, it's good. It builds the final classification map using the data frame from the example image. And taking into consideration that index num column to not lose the geolocation. Yeah, and then just also the reshape. The reshape of the data frame to be then printed outputted on the right of the TIFF. This is the prepared data for the classification that reads the TIFF files here using ArcGDAL. All these pixels are reshaped to a single column. Yeah. And they are also they are stacked like band 1, band 2, band 3, band 4. They are well, the images transform, each of the TIFF of the bands are transformed into a single column, and then they are all stacked so they can be classified to apply in the classification. Yeah, finally is the save the raster as TIFF if you want, for example, to open on QGIS. It's saved as a unassigned integer 8 bits. Then it's just a simple plot of the RGB image side by side with the scene classification. And here I read the band 4, that is the red, the band 3, that is the green, the band 2, that is the blue, and the scene classification map that was saved on the previous step. Change a bit of the brightness of the image. Created the RGB using these 3 separated files. Apply the white to the not the numbers. In this case, it's not necessary to resize the RGB image. And apply a color. This here is a color palette for the scene classification map. 0 is the no data. The marine debris I put as red here in this part here as red. Yeah. So if it's value 1, it needs to be accepted. It needs to be divided by 255. If it's like this, I put as red. This is just the color palette that can be changed. And here is just the side by side of the RGB and the scene classification image. Still compiling or still loading? Okay, perfect. Well, this is what I had to present. I don't know if you have some questions.
Also in the dialogue session, like if we have any general
Yeah. Thank you.